In the previous video we looked at simple harmonic motion. There's another aspect here we need to consider as well, being the energy changes that occur. And just to sort of go back over this idea of energy briefly, recall that energy is basically just the capacity to do mechanical work. In other words, it basically is the ability to apply a force to something and cause a change to occur. Whether that's to cause something to accelerate or to cause it to change shape. So mechanical work, just that idea of applying force. The two types that we're going to look at here, we're going to keep them fairly generic and talk about potential energy. So that's energy that can be stored, and the other one is kinetic energy, and that's the energy of motion. So hopefully you can recall that information. Also useful to keep in mind that potential energy relates to distance or position. So if you think about how, gravitational potential energy, it's how high you lift an object, or elastic potential energy, it's about how far a spring has been either compressed or extended. And kinetic energy depends on speed. How much kinetic energy it has depends on how fast the object is moving. So that's sort of our starting point. The other thing that we need to have a look at here as well is that energy is a scalar quantity. It's important to note that direction is not relevant when you're talking about energy, so it's simply the ability to do something. The direction it doesn't really have any meaning in that sense. Now, in order to look at these energy changes that occur, we're going to consider a mass on spring oscillator. Now, we could do the same with a pendulum. When we're dealing with the potential energy, you'll see that we have a transfer of energy from potential to kinetic and vice versa. We would get the same conversion if we were dealing with a pendulum. It's just that in a pendulum it would be gravitational potential energy, whereas in a spring it's elastic potential energy. But like I said, we're going to deal with just the generic nature of potential energy, so we don't really need to worry about whether it's elastic potential or gravitational potential. And when we're dealing with this situation, to make it a little bit easier, you'll notice here that I'm writing we're going to deal with it on a horizontal frictionless surface. So the effect of the weight of the object's not going to be considered here. Now I'm going to need to draw a few diagrams here, so I'm going to start in the middle. So imagine here's our frictionless surface, and here's the spring attached to some fixed object on the left. So imagine that line on the left represents a wall of some description, so a nice sturdy surface. And to that we've got a spring attached, and that's attached to this mass that can move backwards and forwards. So first thing to note here is that this position that we have the mass located in, that would be the equilibrium position. So that's the point at which all forces on the object are balanced. So there's nothing's been done to the spring yet, it's just resting in its natural state. That means then that we can, if I sort of draw below that, so same scenario but just using a bit of space to represent the different stages of this spring. So if we then take that spring and stretch it out a little, we would then say that the object, or the spring itself, has been stretched. So we can notate here that the stretched spring will store potential energy. So we've put some energy into the system, we've done some work, and so the spring now has energy stored in it, and obviously the next thing is to let it go, and what we would see then is that the object's going to then start to move to the left, so that as it passes through the equilibrium position it's going to be moving to the left, so it's going to have some velocity going to the left there. So if we look at the transition then, so if we work our way back up here, we're going to see that the potential energy has been converted to kinetic energy. And if we continue to follow the path of this object, it's going to continue to move to the left, but instead of just sort of moving without any hindrance, we're going to see then that the spring itself will then start to compress. So that spring is going to be much more tightly compressed, and so the object is now to the left of the equilibrium position, and if we continue to move up there, the kinetic energy has been converted back to potential energy. Note again, we don't have any direction associated with the energy here. It's simply the amount of energy that's been stored, and so we're not really identifying here that there's a left and a right when it comes to energy. It's just whether there's energy that has been stored that will allow the object to do work or not. So that's if we work our way from the rightmost position to the left. Obviously it's going to then move back the opposite direction, and so we can see that these transitions will also occur in the opposite direction here as well. Now that we've got the idea of the conversions of energy that are occurring, we can have a look at where we see the maximums for kinetic energy and potential energy, and it should hopefully make sense if you think back to displacement and velocity. Where we have the maximum velocity, we should there see the maximum kinetic energy as well. And we know that the maximum velocity occurs when the object is in the equilibrium position. So we can see in the middle then that we're going to have the position with maximum kinetic energy is when the object is in the equilibrium position as well. And because it's in the equilibrium position, there's no displacement of the object, and so that's where we'll see zero potential energy. And again, recall that when we're dealing with potential energy, we're looking at the distance that something has moved. So we can see down in the bottom, because the object has moved a distance, that's where we're going to see maximum potential energy. And again, thinking back to the velocity versus time for simple harmonic motion, when we have maximum displacement, we have zero velocity, so that's where we're going to see zero kinetic energy. That same idea is going to apply whether the spring has been compressed or extended. So we're also going to see up in this top position that we're going to have zero kinetic energy and maximum potential energy. Now when it comes to the syllabus for SL, you only need to be able to describe these energy changes. You don't need to do calculations. That will be covered in HL for Unit 9. But at this stage, that an understanding of the energy conversions and being able to describe what happens as the object is moving, that's all that's required for Unit 4.